The quiz is not open notes, no. Back to regular, back in the day, pen and paper, no notes. Okay, again, good evening. I see people jumping on in here. So again, if anybody has specific questions that they would like to go over, you can go ahead and type them up in the chat. Like if you want to go over a difference quotient problem, or if you want to go over a piecewise function problem, if you have something in particular you want to see, you can go ahead and type it in the chat. Because honestly, like, I need somebody to at least give me something to get started. So again, take another minute or so to kind of think about that. While I just kind of see if anyone else wants to join us. So again, guys, thanks for coming. It's good to see you. I would love for somebody to, ask me a question to get started here. Okay, so just to check, guys out there, you can see me and hear me, yes?
Yes, we can hear you.
Okay. All right. So there was a request for, let's see, creating equations from piecewise functions. Okay. So let me go ahead and share my screen here and let me see what I can find. I don't think I need any sound, but I'll do that just in case. All right. So let me go ahead and open up Delta Math here. See if I can find us a problem. All right, so this is a super simple one, but we'll go ahead and start with that. And I'll go ahead and I'm creating a page here in Teams so that you can kind of see my work and follow along with me here. And then again, you can always go back and refer to it. So again, guys, now that I've shared my screen, let me just go ahead and check one more time. You guys can still hear me and you can see my piecewise function. Just somebody say yes.
Yes.
Okay, thank you. Okay, so again, this is a relatively simple one, but it doesn't hurt to start with an easy one. So here, if you're talking about writing a piecewise function, you again have to identify the two pieces. So I have one piece here in blue, and then I have a second piece here in orange. So you have to give this piecewise function a name. You can call it f of x, you can call it g of x. I believe on the test, I tell you what to call it, but you have to give it some name. So let's say that we're starting by looking at the blue piece. Now, again, for a lot of the examples that we did in class, we always did all real numbers where the graphs went on and on forever in both directions. These examples on Delta Math don't always follow that, so they're a little bit different, but I think it's fine. Does anybody want to try? Anybody looking at that blue piece think they can tell me what the domain is? So from what x to what x does that blue piece exist? Just go ahead.
That would be -5 to... Well, actually, -3 to 0.
Okay, so -3 to 0. So that's for the first piece. And so there's an x in between. Do you want equal to's or no?
Yes, because the points are filled in.
Okay, good, perfect. So the first piece exists from -3 to 0, including -3 and including 0. Does somebody else want to try the domain for the orange piece?
0 and 3.
Okay, 0 to 3, good. And both of those are going to be without the equal to. And again, we've mostly done ones where they went on and on, but whether they do or not, it really doesn't matter. The easier one to write the equation of, actually both of these, I guess, are equally simple because both of them have the y-intercept. So for the blue piece, the y-intercept you can clearly see is 6. So that's how I know this is going to be +6. The y-intercept of the orange I can clearly see is -5. So I know that that's going to be linear. Then I'm trying to look at the slope. So if I'm going to try to find the slope, I can take any 2 points, whether they are clearly delineated with a circle or whether I just kind of want to count it. I think that this looks like a point here as well. So it looks like I'm going down 1, right 1. So that has a slope of -1. Be careful not to forget the negative. And then because of the fact that you want it to be aligned, it has to be -x plus 6. For the one in orange, it looks like there aren't any points in between the beginning and the end that meet up on, that actually intersect the boxes. So I'm just going to go ahead and use these 2 points. So does anybody think they can count the slope and tell me what it is?
1/3.
Looks like 1/3. So I would say that that is a pretty accurate looking answer here. Again, I think it easiest to start with the domain. Are they between two values? Are they to the left, to the right? How many pieces do you have? In this case, there are two. For anything that's constant, that should be easy. Again, a constant piece just looks like this. So whatever the y value is, you would just go ahead and choose it. For anything that's linear, you have to first try to figure out what the slope is, then try to figure out what the y-intercept is. So whoever asked this question, is there questions about the pieces of the piecewise functions, or are you looking to see a harder one with harder pieces? Or for anyone?
I was just asking to see the example of just creating one.
Okay, let me see what else I have here, if there are any that are a little bit more challenging. These all look to be linear. Let me see if there is a...
We have to show our work finding the slope, or just count.
I don't, if you can, again, these are pretty simple. So if you're able to do that without showing any work, it's fine. Again, I think it's pretty clear on the test. It says which ones you have to show work for. And of course, there might be some where you don't have to. I'm just trying to see if I can find any, okay, that are a little bit quadratic. So here's one. This is one that's just asking you to find f of 2. But in case anybody wants to see a harder one, this might be a good one. So again, I'm just copying and pasting this all into my class notebook page so people can see. So this is a very similar scenario, except for the fact here that there's part of a quadratic, which I think could certainly be helpful. So again, let's call this one something. I'm going to call this one G, but you can call it whatever you want. There are two pieces here. There's an orange piece and there's a green piece. And again, I would go ahead and start by trying to see if I can figure out what the appropriate domain is. So does anybody want to try to tell me what is the domain of the orange?
-5 to 2.
-5 to 2. And can you tell me what kind of symbols you want?
Between -5 and x should be greater than or equal to, and then the other one should just be less than.
Okay. And so it seems like we're kind of getting better at the domain part. So I would say that the next one is from 2 to 5. And you're going to have an equal to on the 2 because of that closed circle. Just out of curiosity, if I did say what is f of 2, can anybody tell me what f of 2 is?
-4.
Okay, good. And again, you're going to use the closed circle, not the open circle. So then you have part of a line and you have part of a quadratic. Both of these should be relatively easy for you to do, but I would say the line is probably easier. Anybody want to try it? Anybody think they can just tell me what the equation of that line is based on where the y-intercept is and what they think the slope is?
It's x plus 1.
Okay, does look like x plus 1. Good. And then the second piece is a quadratic. Now remember, a normal quadratic goes through 0, 0, and then is the point 1, 1, 2, 4, -1, 1, -2, 4. So there are some pretty clear transformations that happened here. Again, this is x squared. Can anybody tell me what's one transformation?
The graph moved to the right 4.
Okay, anybody see a different one?
The graph also is a reflection.
Reflection where?
On the x-axis.
Okay, and then whoever's talking, you want to see if you can tell me what the equation is? Like, how do I take this and turn it into an equation that goes here? Or if you don't want to, does anybody want to try it?
I think it's -x squared minus 4.
So the negative is right. And then tell me about, like, do you want it, you want this? Or do you want...
Put that in parentheses.
So this?
I think so, yeah.
Okay, I think so too, right? And so then here's the thing. I told you, you guys, there might be a stretch or a shrink. If it's part of a piecewise function, I probably am not going to make it a stretch or a shrink. So chances are that would be the right answer. What's a really quick way that I can double check if this is right or not? Anybody know?
plug in the x and y values?
Yeah, plug in a point. If you plug in 2, you're supposed to get back -4, which if you plug in 2, you do get back -4. If you plug in 3, based on the graph, you're supposed to get back -1, and that works as well. So again, little tip for you, I would imagine that if you're seeing a piecewise function, it probably isn't going to be anything super complicated. So again, I would double check after you've put the transformations in to see if that's it. I would imagine probably it will be. If not, I would just go ahead and try some stretches and some shrinks. In this case here, it might behoove you to just put in a 2 or a 3 or a 4. But I would imagine if it's part of a piecewise function, it should be pretty straightforward. So I think those were 2 actually great questions. Piecewise functions we did spend a lot of time on. So we now did 2 examples where I gave you the graph and you made the equation. Does anybody have any questions about how you go in reverse? Any issues? Whereas if I was to give you this and ask you to make the graph, anybody doesn't think they could do that or wants to ask a question? Okay, let me go back to the meeting here. Let me see if anybody typed anything else. So that was the only official question that somebody asked so far. So if anyone would like to ask something else, you can either just say it or you can go ahead and type it.
I would say finding zeros with technology and finding maximum and minimum values with technology.
So that is not something you have to worry about for this first assessment. It was in the Delta math, but that's not something that we really spent any time on so far this chapter. You're going to see a whole lot of that in chapter 2. So that is not something that you have to worry about for this assessment.
Can you go over the difference quotient?
Sure. So the difference quotient, which I call the DQ for short. So I'll start off with an easy one here, just in case. So let's say that I give you the function 2x plus 5. And again, I have to give you an f. So let's say that I'm deciding to make it 2x plus 5. And then the difference quotient can either have x's and h's, or it can have x's and numbers. We've mostly been sticking to the ones that have numbers, so I would imagine that that's probably what you're going to see. So let's say that I ask you to find f of, or the ones that have numbers and h's rather. So let's say that I ask you to find f of 2, no, not 2. Let's say f of 7 plus h minus f of 7, all divided by h. So again, just to be 100% clear, if this was a question on the test tomorrow, I would have to give you both of those things. I would have to first tell you what equation do I want it to be. That's the f. I would then have to tell you what is it that I want you to calculate, and that's the red. So first of all, in this difference quotient, this h is just an h. That h should always cancel out at some point, 100% of the time. That's kind of the whole point of the difference quotient. Then you have this yellow, which is its own calculation. You might want to think of this as being in a parentheses. And then this f of 7 is a separate calculation. And then the minus in between, it's always going to be a subtraction. So I'm going to start by finding the yellow, which means I'm going to go to the f function. Everywhere there's an x, I'm going to put a 7 plus h. So this would be 2 times 7 plus h plus 5. So again, I took the 7 plus h, I went to the function. Everywhere there's an x, I put a 7 plus h, and then don't forget about the plus 5 because it has to be a thing. So this is the calculation that happens if I just do the yellow. Then again, there has to be a minus because that's what the formula says. I know that this is all still over h. And then I want to find f of 7. So f of 7 means go back to the f function. Everywhere there's an x, you're going to put a 7. So 2 times 7 plus 5. Either whoever asked me the question or whoever, or anybody, does anybody have a question so far? Okay. So then I'm going to go ahead and try to calculate this. So I'm going to go ahead and distribute this too. So that's going to give me 14 plus 2h plus 5. When you're doing a number, I think it's easiest to calculate the number first and then subtract it. You could distribute if you want to, but I actually think that this is easier. So 2 times 7 is 14, plus 5 is 19. So this is going to become minus 19 all over h. Again, most of the ones we've done in class have been quadratics. This is a linear, so I'm just starting you off nice and easy. From this point, though, a lot of things should cancel, and they should always cancel in a similar fashion. So here, this 14 plus 5 is 19. Minus 19 means that all the constants are going to cancel, and all you're going to be left with is 2h over h. If you have an h on top and an h on the bottom, you're going to go ahead and reduce just to be a 2. So again, you probably want to see a harder one, which is fine, but this is showing you an easier one just to make sure you understand the mechanics. So, questions? Okay, let's say that we wanted to do this same exact problem, but let's say instead we now want to do it for f of x equals 2x squared plus 5. So we want to do the same calculation here, but we want to do it for 2x squared plus 5. You're going to do it in a very similar fashion. The difference being is now because of the squared, you're going to have foiling to do, which means you're ultimately going to have a little bit more work, but it's the same idea. So starting with f of 7 plus h, everywhere there's an x, you're going to go ahead and put a 7 plus h. So that's going to be 2 times 7 plus h, the whole thing squared, plus 5. Then it's a minus. You're going to go to the f function, and everywhere there's an x, you're going to put a 7. So 2 times 7 squared plus 5 all over h. So again, before we even finish the calculations, just again, take a look. Over on the left-hand side, the one that we already did, because it was just linear, that means that I wound up with a very simple answer, which in this case is 2. The fact that this is a quadratic means it's going to be a little bit more work, and I'm going to wind up with a slightly more complicated answer, but the idea of plugging it in should be the same. So any questions up until that point? Okay, so now we're going to go ahead and actually do it. And again, this right here, this is a FOIL. So I would hope that we're kind of remembering that. So the 2 is on the outside. 7 plus h times 7 plus h. If you have to write the whole FOIL out, that's fine. 7 times 7 is 49. The outers is 7 times h. The inners is also 7 times h, which is going to be 14h, plus h squared, plus 5. So again, that is still this yellow piece right here. Then minus, if I do 7 squared, so 7 squared is 49. 49 times 2 is what? 98. Plus 5 is 103. All over h. Any questions to here? Okay, so then now I have to distribute this 2. So if I distribute this 2 times 49 is 98, plus 28h, plus 2h squared, plus 5 minus 103, all over h. Just like before, 98 plus 5 minus 103, that should cancel. It should always cancel out completely. If it doesn't cancel out completely, you know that you've done something wrong. So now you have 28h plus 2h squared. You can now go ahead and reduce an h from each of these places. So if you reduce an h on the top, you get a 28 plus 2h, and that actually is your answer. You are not going to go any further than that. You're not going to set it equal to anything. You're not going to solve for anything. You're only going to go as far as you can, which in this case is 28 plus 2h. There eventually is a lot more that you can do with it, but for now, that's as far as you have to be able to go. So give people a second in case they're copying that down. Questions? No? Okay, hang on one second. Just checking. Does anybody see a mistake? I think it's okay, but I'm just making these up as I go, so I'm just making sure. Okay. Questions or more types of things that anybody would like to see?
I think there's a question in the chat.
Okay. Go back. So I have a lot of windows open. Determining if x is a function when there is a y squared. Okay. So it's a good question, although there isn't really a lot to do with it. If I'm going to, so again, first of all, let's just remind ourselves, what is the definition of a function? Is that every x has exactly one y. So there are like lots of easy ways that I could ask you to tell me whether or not something is a function. If I were to give you a graph, you could just perform the vertical line test and you would be able to see whether something is a function or not. If I was to give you a table, you would be able to look at it and tell me, because this is a small function with only 3 values, because none of them go to more than one place, this would be, yes, it is a function, where this fails the vertical line test, so it's a no. If I ask you from an equation if something is a function, you're basically looking for something to be weird with the y. Anytime you have regular x's that you're used to, any combination of being linear, any combination of a quadratic, any radical, any cubic, these are all always going to be functions. For something to be easily identifiable from an equation to not be a function basically means you have one of two things. There are others, but we're going to mostly see these two things. The first of which is that you're going to have a y squared. If you see a y squared, it's not going to be a function because of the fact that you're going to have a quadratic that either faces left or right. That will fail the vertical line test and will definitely not be a function. The other main thing is if you see an absolute value around a y. When you see an absolute value around an x, it faces up and down. When you see it around a y, it faces left or right. So generally speaking, if you have an equation that has a y squared or an absolute value of y, that is how you know that these are not going to be functions. Anything else, if you just see a y by itself, you can feel pretty confident that it is a function. So it's a good question, but not a huge priority for tomorrow. And again, even if it were, there aren't very many types of problems I can ask you where you have to be able to just be able to look at it and tell me yes or no. So if you understand what I just went over there, I think that's more than enough for tomorrow. I don't think that you have to worry too much about it unless whoever asked the question can ask me like a follow-up. But basically, like, it's yes or no. And anytime you see a y squared, it's no. Okay, these are good questions. What else? Okay, I see some people typing, so I'll give you a minute. So going over graphing stretches and shrinks, like, can you be more specific? You can say it if it's easier, like a particular function, or like can a little bit more about what you're looking for about stretches and shrinks? Okay. I mean, I can pull that up on Desmos here. I know that there's a lot of those. So like, okay, let's see. All right, so those I think are just rigid. Okay. So the square root of 1/3 x plus 3. Okay. So if you were going to try to graph the square root of 1/3 x plus 3, you basically want to think of this as like a series of transformations. The first of which means you have to start somewhere. So like, you know that you have the square root function, which goes through 0, 0. You know that it goes through 1, 1. You know that it goes through 4, 2. So 0, 0. 1, 1, 4, 2. That's my quadratic. You now want to do two different changes to it. You want to do this 1/3 x, and then you want to do this plus 3. So this is an x change, which is a horizontal stretch. Then this is a y change, which is up 3. The fact that one of them is a horizontal stretch and one of them is a vertical change means that you can do either one first. It doesn't matter, but I'll do them one at a time. So like, if I want to take this graph and I want to horizontally stretch it by 3, that essentially means I'm going to take each of these points and I'm going to multiply the x values by 3. So if I take the point 0, 0 and I multiply the x value by 3, it is still going to be at 0, 0. If I take the point 1, 1 and I horizontally stretch it by 3, that is now going to become the point 3, 1. If I take the point 4, 2 and I horizontally stretch it by 3, that's now going to be 12, 2. So this is what happens if I just do the horizontal stretch. If I then now want to take this entire graph and I now want to move it up 3, I'm going to take each of those points and I'm going to move it up 3. So if I take 0, 0 and I move it up 3, that becomes 0, 3. If I take 4, 1, that now becomes 4, 4. And then 12, 2 becomes 12, 5. No, yeah. And then that would be the final product. And again, because I'm just eyeballing it, it doesn't look absolutely perfect. But if you compare where you started with to where you ended, I mean, it looks like it's rising less quickly, which is the case because of the fact that you stretched it out. I hope that answered the question for whoever asked it. But let's say you want to see just like a couple more with like a stretching and shrink. So let's see what we got here on Desmos. So again, this is an exponential. Exponentials are not on the test tomorrow, so like I'm not going to worry about those. But if you take a look here you have the 1/3 on the outside, which basically means you are vertically shrinking the y's by 1/3. So you would take each of these y values and you'd multiply them by 1/3. The easiest one to do is probably this one here. If I multiply that y value by 1/3, it shrinks from 3 to 1. And notice that all the y values went down by 1/3, and that's like what I'm looking for. What else do we have here? Again, exponential, those are not tomorrow. 2 times the square root function, again, would mean you're taking each of these x's and you're doubling them. So this 3 becomes a 6. The nice thing about Desmos is you can just kind of drag them, where obviously if you have to do them pen and paper, it takes a little bit longer. But essentially that's what it's asking you to do. So 1/4 x squared. Can anybody tell me, does that 1/4, is it a vertical stretch, a horizontal stretch, a vertical shrink, or a horizontal shrink?
Vertical shrink.
Vertical shrink of 1/4. So every y value gets multiplied by 1/4. So this 4 becomes a 1. And again, they all have to move together. So notice that it's shorter than it was originally. It also looks wider, but for some functions, wider and shorter kind of look the same. So again, as far as stretches and shrinks go, you kind of just have to remember which one is on the outside and which one is on the inside. Can you do a graphing piecewise function example? Okay, I think that means if you can graph it from the equation. So again, if we go back to piecewise, so those are both linear. Let's see if I have something a little harder for you. Okay, so this is good, although maybe I'll change it a little bit just to make it a little bit more challenging. Okay. All right, so let's say that I wanted to graph this piecewise function. Again, each of these 3 values here represent the 3 different pieces. So 1 in green, 1 in orange, and 1 in blue. Just to kind of bump this up a little bit, why don't we make this a negative x squared? Just because I think you're probably likely to see part of a quadratic. So why don't we go ahead and just make it that? That way we can see a harder example. So I'm going to go ahead and start with what I think is the easiest piece. So the easiest piece I actually think is the orange piece in the middle. You're going to be graphing the constant function 1 from -2 to 2. One of them is included and one of them is not included. So if I plug in this -2 into my constant function, that is going to be the point -2, 1. And I'm going to do that as an open circle because of the fact that there's no included. Whereas if I plugged in this 2, I would also get back 1, but that is going to be a closed circle. Every value between them is just going to give me a value of 1. So the piece in the center is simply a constant. If I go now to do -5/2 x minus 4 for x is less than or equal to -2, I'm going to start by plugging in -2. Whatever I get for that y value, I'm going to draw it as a closed circle. So when I plug in -2, -2 times -5/2 is +5, minus 4 is 1. So that means that at -2, 1, I'm going to get a closed circle. And remember, if you have an open circle on top of a closed circle, you just draw it so that it looks closed. You're only now going to graph this to the left because you're only graphing less than or equal to. So that means the slope of -5/2, you're going to go up 5 and left 2 as many times as will fit on your graph. And then again, for the final piece, I made it a square just because I think that it's a little more interesting that way. You're going to go ahead and start by plugging in 2. So if you go ahead and start by plugging in 2, you would first have to square the 2 and get 4, then make it negative, which would be -4, plus 4 is 0. So that means that 2, 0 is going to be open. Then you have to plug in values to the right. So things that are bigger than 2, let's say you plug in 3. 3 squared is 9. If you make it negative, it's -9. Plus 4 is -5, so 3 -5. If you plug in 4, 4 squared is 16. -16 plus 4 is -12. So that's going to be somewhere around here. And again, when you connect them, it should be curvy because it's part of a quadratic. Again, it's hard to, I just made it up from scratch, but this should be a curve because it's part of a quadratic. So again, another good question. Let me go back to my chat and see if I have anything else here. Okay, I'm not seeing anything typed up. So does anybody want to type something? Does anybody want to say something out loud? Does anybody want to ask a question? Go back to my chat here. I mean, even if people don't have specific questions, does anybody just have any general questions about the test tomorrow? Again, it's 15 questions. It is 65 points. You'll get all 50 minutes, so try to get to class as soon as possible. You can use a pencil and a graphing calculator. You cannot use any notes or anything, though, so that is different than the past year and a half. What else, guys? Any other types of questions that I can answer for you? No? Anything? I mean, again, I think it's a pretty fair test. I think, yes, there's partial credit, of course, always partial credit. What I would recommend and what I will tell you tomorrow as well is that, you haven't taken a pen and paper test in a while. So if you come across a question that you genuinely have no idea how to do, you should skip it. And then keep working on the stuff that you know the best to ensure that you try to get the most credit as possible, and then only go back if you have extra time. But yes, there is partial credit. There's always partial credit for math, so certainly. What else?
Partial credit means extra credit, right?
No, partial credit is not the same as extra credit. Partial credit means, is it 100% right or 100% wrong?
Oh, okay.
So like if a question was worth 5 points, you can get anywhere from 0 to 5 points, depending on how much of it you get correct. Okay, anything else? I mean, I have to say, I took the test earlier today just again to look at it. I think that a lot of the questions you guys asked are helpful. I think graphing piecewise functions are helpful. I think writing equations of piecewise functions is good. Talking about the transformations is good. Make sure you know, just generally speaking, if you see, just y equals mx plus b, you have to know that it's a diagonal line. If you see just a constant, you have to know it's a horizontal line. If you see a squared, you think the U shape. If you see the square root, you think the scoop shape. If you see those double bars, the greatest integer function, make sure that you know that means the staircase. So just because we didn't go over it right now in this meeting doesn't mean it's not on there. But again, you want to make sure that you have a working knowledge of all the different functions. So difference quotient is a good idea. You might want to review just the basic function analysis of a graph. Make sure you can find whether it's increasing, where it's decreasing, where it's constant, where are the x-intercepts, the y-intercept, domain, range. Is it odd or even? Does it have y-axis symmetry or origin symmetry? Those are all things we've talked about a lot of the days. So I think that that's good. Domain and range from a graph, from an equation. I think those are good places to kind of focus your efforts. So other questions that I can answer for you about anything? I mean, don't be shy, but I'm not going to just sit here. So if no one has questions, we'll end the meeting. But if anyone has anything else, I'd love to hear it. Okay, well, at the very least, I hope that you got something out of it. Okay, so identifying origin, y-axis, and x-axis. Do you want that from the graph or do you want it from an equation? An equation, okay? So let's go back to that. All right, so before we get back to that, again, so there's even functions, there's odd functions, and then there's neither. If you're talking about being an even function from a picture, you're talking about a graph that has y-axis symmetry. Not a great graph on my part, but here would be an example of an even function because it has y-axis symmetry. If you're talking about an odd function, then you are talking about a graph that has origin symmetry. And if you're talking about a graph that's neither, that would mean that it had neither of those symmetries. So here's an example of a neither. If you're talking about finding symmetry, right, from an equation, there are 3 different tests. There's a test for x-axis symmetry, there's a test for y-axis symmetry, and there's a test for origin symmetry. So the tests are as follows. If you're trying to test for x-axis symmetry, leave the x alone, but make the y negative. If you're trying to do y-axis symmetry, make the x negative. If you're trying to do origin symmetry, you're going to make them both negative. Then I have to give you an equation. So let's say that I gave you the equation y equals 2x cubed plus x, or plus x. If you wanted to test this for x-axis symmetry, in the equation, everywhere there's a y, you're going to turn it into a negative y. So negative y equals 2x cubed plus x. You would want to see, is there any way that I can take this new equation, and is there any way that I could turn it exactly back into the original problem? The only way that you could do that would be if you divided everything by a negative. If you divide everything by a negative, there's no way that you can go back to the original problem. So the fact that you can't go back to the original problem means that no, there is no x-axis symmetry. If you're trying to test for y-axis symmetry, it means that everywhere there is an x, you're going to make it negative, and you're going to see if you can go back to the original problem. So everywhere there's an x, which means y equals 2 times negative x cubed plus negative x. If you cube a negative, it becomes a negative 2x cubed minus x. And then again, you would want to check this compared to the original. Is there any way to make it go exactly back to the way that it started? Again, the only way you could do that is if you divided everything by a negative. But if you do that, you're still not going to be able to go back to the original. The final is for origin symmetry. So for origin symmetry, you're going to make the x and the y negative and see if you can get it to go back. So if you make the x and the y negative, you're going to get negative y equals 2 times negative x cubed plus negative x. This negative y stays a negative y. If you cube a negative, you get negative 2x cubed minus x. You then want to see, is there any way to take this and turn it back to the original? Again, the only thing you could do is divide everything by a negative. And if you divide everything by a negative, everything is going to turn back positive. So the fact that you were able to get this to go back to the original is why you would say, yes, there is origin symmetry. So again, just in summary, these are the 3 tests. For x-axis, make the y negative. For y-axis, make the x negative. And for origin, make them both negative. After you perform the calculations, if you are able to somehow get them to go back to the original, then the answer is yes, which in this case, it was only for the origin. If you are not able to get them to go back to the original, then the answer is no, which is why it was no for x and y. But again, very important, you also know, graphically speaking, how to find it and whether or not it's odd, even, or neither. Okay, good questions. Anything else? Okay, well, I'm going to stay here till I'm the last one. So if you feel like you got something out of it and you feel like it's been helpful, then you're welcome to exit. If anybody has questions that they were just too afraid to ask, you can stay until I'm the last one. And I would just make sure you try to review as best you can, and I will see you tomorrow. Anyone else? All right, thanks, guys. Shane, any questions for you?